I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
What if we could create a perfect virtual copy of every laser, telescope, or optical circuit, one that thinks, reacts, and evolves alongside its real counterpart? Welcome to the era of digital twins in photonics, where light meets data and reality meets simulation. Across research labs and advanced industries, engineers are now building living digital replicas of optical systems, from fiber networks to space telescopes. These aren't just computer models, they're dynamic systems fed continuously with real-time data, learning and predicting how light behaves inside the most complex devices on Earth and beyond. So, what exactly is a digital twin? Imagine pairing every physical system with the digital version that updates every time the real system changes, like a mirror that doesn't just reflect light, but understands it. Originally developed by NASA to simulate spacecraft during Apollo missions, digital twins have evolved dramatically thanks to artificial intelligence, high-performance computing, and the Internet of Things. Now, in photonics, the science of controlling and harnessing light, this concept is unlocking a new era of precision and prediction. Photonics powers everything from the lasers in manufacturing to the sensors guiding self-driving cars, the optical fibers carrying our internet, and the imaging systems used in surgery. These technologies demand nanometer-level precision, and that's exactly where digital twins excel. At the heart of every photonic digital twin are four elements working together. There's the physical device, a laser array, an optical sensor, or a telescope mirror. Then comes the virtual model, a detailed simulation that captures how light interacts, reflects, and refracts across its surfaces. Real-time data flows in from sensors, monitoring temperature, vibration, and signal quality. Finally, AI algorithms process that data, detecting patterns, predicting problems, and even suggesting corrections before failures happen. This constant feedback loop allows engineers to test, tune, and optimize systems without ever touching the hardware. In fiber optic communications, digital twins can predict when a signal will degrade, automatically adjust routing, or rebalance bandwidth before users ever notice a slowdown. In imaging systems, they simulate how photons scatter or interfere, helping doctors get sharper, more reliable scans. And in LiDAR, the light-based radar guiding drones and autonomous vehicles, twins let designers test thousands of environmental conditions virtually, from dense fog to bright sunlight, ensuring real-world reliability. The real magic happens when these digital twins merge with artificial intelligence. Imagine a self-learning laser system that senses performance drift and recalibrates itself on the fly, or an AI that analyzes trillions of photon interactions to fine-tune quantum circuits. That's already happening in research labs today. At MIT and Nokia Bell Labs, for example, scientists developed a photonic neural network whose digital twin continuously learns, adjusting optical pathways in real time for ultra-fast computing. And in Europe, researchers at EPFL created a twin of a quantum photonic processor that predicts interference patterns with over 99% accuracy, a massive leap for quantum communications and computing. And even in space, digital twins are redefining what's possible. During the deployment of the James Webb Telescope, its digital twin acted as a virtual mission control, mirroring every hinge, mirror, and actuator as it unfolded 1 million miles from Earth. It processed hundreds of millions of data points daily, allowing engineers to visualize, in real time, what no camera could see. That digital model turned risk into precision, ensuring perfect alignment of one of humanity's most ambitious optical systems. Down here on Earth, photonics manufacturing is also transforming. Producing photonic chips, waveguides, or laser components requires atomic-level accuracy. Digital twins let manufacturers simulate entire production lines, predict coating thicknesses, and correct alignment errors before they occur. The result? Faster prototyping, lower cost, and near zero defects. In telecommunications, digital twins are creating self-healing optical networks. A 2024 field trial by Infinera and Deutsche Telekom showed that AI-powered twins could predict nonlinear distortions across a 1,200-kilometer fiber span and automatically reroute signals, reducing downtime by 76% and cutting energy used by a third. And as photonic systems evolve toward quantum and neuromorphic architectures, we're seeing the rise of cognitive twins, digital counterparts that don't just monitor, but think. They can learn from data, adapt to new operating conditions, and optimize performance autonomously. In effect, these systems make light itself part of a living, intelligent feedback network. Looking ahead, the convergence of digital twins, AI, and quantum photonics could give rise to what some researchers call a photonic metaverse, a fully simulated ecosystem where every optical component, from a telescope mirror to a city's smart lighting grid, exist in both digital and physical form. Imagine designing entire photonic cities in the cloud, optimizing every reflection, signal, and beam before construction even begins. The implications stretch far beyond engineering. In medicine, digital twins could represent a patient's eye or vascular system, enabling surgeons to perform virtual optical procedures before operating. In defense, they're already modeling high-energy laser systems and advanced surveillance optics for faster, safer mission planning. Engineers can simulate laser propagation through various atmospheric conditions, study beam dispersion and heat effects, and optimize sensor performance, all without risky, expensive field tests. These systems allow mission planners to visualize complex optical engagements in detail, improving precision and reducing uncertainty in real-world operations. Of course, challenges remain, from data security to the massive computing power required to simulate light-matter interactions at quantum scales. But progress is rapid. As these technologies mature, we're moving toward a world where every photonic system, every laser, lens, or optical chip has a living, learning twin. In the end, digital twins are doing more than refining photonics. They're transforming how humanity interacts with light itself. By blending physics, AI, and imagination, we're not just observing the future, we're building it, photon by photon, in both the real and the virtual worlds. Thanks for watching. Subscribe, follow, or visit idsth.com for more cutting-edge defense and tech insights. See you in the next one.